Welcome everyone to my talk at SIGCOMM. I'm sorry I can't be with you in person to deliver this talk, but I'm delighted to be able to share my vision of what's beyond 5G. I'm Andrea Goldsmith. I'm a professor of electrical engineering at Stanford University currently, and I am moving to Princeton University on September 1st to become their Dean of Electrical Engineering, Dean of Engineering and Dean of Electrical Engineering. Sorry, too early in the morning for me. Dean of Engineering and Applied Science and Professor of Electrical Engineering. So what I want to talk to you about today is what's beyond 5G. So I will tell you a little bit about what is 5G and what isn't 5G today, but really I want to look to the future of what future wireless networks are going to be able to enable that isn't possible today. So I've been working in wireless communication my whole career since the mid-'80s when the first cellular systems were rolled out in Chicago. And I actually think that today is the most exciting time for wireless. And the reason is how wireless networks have evolved. So we started back in the 80s with cellular networks that were really just about people talking to each other in a way that they didn't need to be connected to a wall. And as these networks have evolved, we've seen more, obviously, voice communication, but now data communication where we're accessing data from the internet. But what's happening in the next wave of wireless technology is that it's no longer going to be about people talking to each other or accessing information from the internet. We're really going to enable a much larger class of smart devices where people are no longer part of the equation in terms of what the network is trying to do. So we're going to have a lot more device-to-device communication, and that's going to enable things well beyond what we can do today with cellular and Wi-Fi to, for example, making our cities much smarter so that the infrastructure itself can sense what's going on and change the traffic patterns, or if there's an emergency response, or if the trash needs to be collected, it doesn't come to get collected every Wednesday. It comes to get collected whenever the trash can is full because there's sensors in the trash can. We're also going to see a wide range of networks around our bodies and even inside our bodies to control biomedical devices. Enhanced reality and virtual reality, if we can make our networks faster and make sure that the latency is low enough, we'll be able to do virtual reality from virtually anywhere in the world. These are some of the applications that I think are very exciting for future wireless networks, but 5G technology as it's deployed today is nowhere near being able to enable this vision for the next generation. So there's a lot of interesting work for wireless researchers to do. One of the biggest challenges for this vision of wireless networks is the fact that the licensed airwaves are full. So this slide was, this picture was taken from a report by the FCC back in 2013. So it's already 7 years old. And at that time, the growth in demand for data, wireless data, was growing exponentially. It's still growing exponentially. But even at that time, in the licensed airwaves, so the airwaves that are licensed to the carriers, basically we were in, as of 2013, 90 megahertz of spectrum deficit, and it was predicted that we would be in 300 megahertz of spectrum deficit by the following year. And of course, now we're 6 years later than that. So why is it that we're actually able to use our wireless networks, despite the fact that we've used up all the bandwidth, is that we have Wi-Fi. So Wi-Fi is essentially 300 megahertz of unlicensed spectrum in the 5 gig band and 80 megahertz in the lower bands. And that is actually why we're able to use our wireless devices. If we were just reliant on the licensed spectrum, we wouldn't be able to do even any kind of high-speed data downloads, and certainly not video. So Wi-Fi is really what's enabled our networks to work through today. Looking to the future, because the Wi-Fi bands are also starting to get filled, is a whole range of spectrum in the millimeter wave, so that's up at 60 gigahertz and above, and even beyond that, the terahertz bands, which have tens of gigahertz of spectrum, so there is no spectrum shortage up there. In fact, every wireless service today can actually fit into a small part of the millimeter wave band. So there's lots of spectrum up there. But unfortunately, the laws of physics make it very difficult to use that spectrum, and that's one of the challenges that wireless researchers are looking at. Another fun band to look at, or another fun domain to do wireless communication, is molecular communication. So I'm not going to talk about this, but this is some of the work that I've done in recent years, is how do you actually send data using molecules instead of electromagnetic waves. So you use an acid to send a 1 bit and a base to send a 0 bit. And we've actually been able to demonstrate that you can send text messages using molecular communication over a channel, which could be inside the body, or it could be in under the ocean, or any medium that carries chemicals. So if you look at the promise of 5G when it first started being developed, which was about a decade ago, because it takes about a decade to standardize a new cellular system, the thing that was really different about 5G versus prior generations of cellular technology was that every generation, from first generation to fourth generation, was really about just getting to higher data rates. How do we increase the data rate by an order of magnitude for cell phone usage? And then, of course, making our devices more capable of doing different things. What the next generation, or the promise of 5G, would be not just to focus on getting to higher data rates, and the data rates that they're looking at are in the tens of gigabit per second range, which is what Wi-Fi can do. Right now, cellular 4G is on the order of 300 kilobits max rate. So this is, several orders of magnitude higher. But in addition, these 5G networks also aim to allow for very low energy, so that you can put a very low power sensor or large set of sensors out in the environment, and they can connect to the backbone network without using up a lot of battery power. That's not possible today, given technology and also given the protocols for cellular. And the other thing that we need in these next generation of networks is very low latency, so that we can enable things like automated driving and real-time virtual reality and game playing and so forth. Now, putting all three of these capabilities into one network is extremely challenging, and there won't be one device that can simultaneously get 10 gigabits per second and live for 10 years on a battery and have very low latency and ultra reliability. But there will be different devices that are operating at different points of this triangle. So some of our devices, like our cellular cell phones, will require the 10 gigabits, whereas others, like sensors, will require the 10 years on a battery, and things like automated driving will require ultra reliability. So we need to build a network that can simultaneously provide all of the specs on this curve, but not necessarily to the same device. And that's not possible even with the 5G technology that's being deployed today. So 10 gigabits per second on a good day, if you're right next to the base station and you have the most advanced technology, you may be able to get that with what is currently deployed as 5G, but we certainly don't have the low power and the low latency that's promised. And so that's what we need to build out in 6G and beyond. So as a researcher in wireless technology, we are looking at a number of enabling technologies for these networks. And one of the interesting aspects is not just necessarily building better radios, but rethinking the whole concept of cellular system design. So if you look at how cellular networks are designed today, the basic premise was actually written up in a paper by D.H. Ring from 1946. So it's a very old concept of putting a base station in the middle of a cell, and then all the users within that cell connect to that base station. And when you move to a new base station in another cell, then you have a call handoff. All of that was written up in this paper that's more than 50 years old. As technology has evolved, we've certainly utilized that technology in the base stations and in the cell phones, but we haven't really rethought how we should design cellular systems in light of all this new technology. And so in some ways, it's time for a clean slate to think about how we should be designing cellular systems today, given the requirements that we have and given the advanced technology that we have from 1946 when we were still using vacuum tubes. Another important aspect of 5G technology development is using the millimeter wave band, which is challenging because the power falls off very quickly in that band. So if you look at utilizing millimeter wave technology, the way to do it to get around the fact that the signal power falls off as 1 over the frequency squared. So when you go up to these very high frequencies, you get very limited range. And that's why, even though there is a small amount of millimeter wave spectrum deployed in cellular today, you have to be very, very close to the base station in order to utilize that spectrum. So one technology to get around that is to use something called massive MIMO, where you have hundreds of antennas, and they're pointing the energy of the signal in the direction of the device. And so by doing that pointing, you get around this problem of the power falling off as 1 over frequency squared, and you can get much better range. Now, the challenge of using so many antennas is, first of all, this becomes a very complex antenna array. There's a lot of computational complexity. You need to measure the channel very accurately to know where to point the beam, and that entails a lot of overhead. And then if there's scattering in the environment, this beautiful beam dissipates and you no longer have connectivity. So there's a lot of challenges in building massive MIMO systems. Another technique that is being thought about for this rethinking of cellular system design is to do multi-hop routing, so where you might have a relay, also using very small cells to increase the capacity of the system. And when you go to small cells, you can also put caching and computation at the edge in these small cells. So these are some of the things that are being thought of in terms of technology, and also looking at optimizing the network in the cloud. So the way these base stations are deployed today, they're basically put out there in a static manner, and you can actually use dynamic optimization either in the cloud or in neighborhoods of networks and neighborhoods of base stations to optimize how you do your parameter setting so that you can meet the application requirements. So I'm going to talk about all of these things in a little bit more detail in the few minutes that I have left. Now, machine learning obviously is a very hot topic, and it's also a topic that people have been looking at in the context of wireless network design. And so you might say, well, you know, why do we need to work on any of the things on this long list? Why don't we just let machine learning attack the problem of designing cellular systems? Can't that enable everything? And of course, machine learning is a bit of a bandwagon today. And as someone who does communications and signal processing, you know, usually I run away from bandwagons, but I said, well, maybe this is a tool that we might want to utilize in communication system design. So rather than running away screaming, maybe we should actually look at where this tool might be useful in designing communication systems. And so we've actually done some work on using machine learning in the design of physical layer, so just getting bits from the transmitter to the receiver. And it turns out that machine learning is a very powerful tool. It can do better than the theoretically optimal technique of Viterbi decoding when you're trying to equalize a channel that you don't know, or that has unknown parameters, or that you have a computational complexity constraint. So we started looking at this in the context of molecular communication, because as a diffusion process, there's no model for that channel, and we did better than existing techniques. So then we started looking at using machine learning on traditional channels, electromagnetic wave channels, and we also did better when there was a complexity constraint or the channel was unknown. So we have shown that there is a role that machine learning can play in physical layer design. The question is there a role for machine learning in higher levels of the network protocol design? So network resource allocation has been an NP-hard problem, even going back to the second generation of cellular in terms of how you allocate frequencies to users. That's an NP-hard problem. If you start looking at networks today, where we have many more challenges of large cells and small cells and heterogeneous devices and heterogeneous applications, this resource allocation problem becomes intractable. So maybe machine learning has a role to play there. But it is a hard problem to formulate as a machine learning problem. So we haven't actually figured out how to formulate the problem, but it is something that may be promising for applications of machine learning. Distributed learning, if you're trying to do a sensor network application where you're trying to learn some parameter of the overall environment from massive sensing, may be able to do that through distributed learning. And cross-layer design, where you're trying to meet the requirements of an application through lower levels of the network supporting that application, also something that's been an intractable problem for decades in communication theory. So maybe machine learning has a role to play there. So I want to return to this notion of rethinking cellular system design. The idea of that paper that was written in 1946 is that you design this system so that you reuse frequencies in a way where your system is interference limited. So it's the interference of neighboring cells that are using the same channels that you are that determine how good your performance can be. And now that we have all these advances since the 1940s of doing signal processing to cancel out interference, using antenna arrays to point beams away from interfering nodes, we no longer have a system that's interference limited. So this gives us an opportunity to rethink how we design these cellular systems. There's also many technologies that have been introduced into cellular over the last few years, like having base stations cooperate, having these small cells, because small cells can actually provide exponentially larger capacity than having a large cell, distributing the antennas through distributed antenna system, or DAS, where now you have the antennas much closer to the radios, and therefore there's less energy required, and also using relaying between base stations and also between devices. So there's many technologies that have been integrated into cellular system design. The only one of these that has really taken off and become widespread is small cells. And so I'll talk about those in a moment, but basically when you're asking the question for this new vision of cellular, how should these systems be designed? Perhaps we shouldn't just be looking at capacity in terms of data rates, but maybe we also want to look at coverage or energy consumption. Coverage, you know, I live, my house in Menlo Park is right off Sand Hill Road. I can't even make a phone call driving up Sand Hill Road, so I don't even get decent coverage for voice. That's going to become much more of an issue when we're using these networks for automated driving and applications where we really need reliability. So I said small cells are the solution to increasing cellular system capacity. We're starting to see small cells getting deployed widely in 5G networks, and that is due to the capacity gain. But we're still going to have large cells as well, because we need that for coverage. That's how an operator rolls out their network, is they put up large cells with the new technology, and then they go to the small cells. So basically this notion of doing computation in the cloud to manage between the large and small cells is one of the interesting technologies that we've actually looked at, which is cloud optimization. So the idea is that if we want to optimize our resources across these different large and small cells, we can put the optimization in the cloud, but that gets very complex. It's an NP really hard problem, because it's not just NP hard, but we have many, many other parameters that we need to deal with. And there is advanced optimization tools that we can use, but what we've actually been looking at in addition to those tools is using this fog-based optimization, where we take neighborhoods of nodes and we do the optimization there. As the neighborhood grows, it becomes centralized optimization, and as it shrinks, it becomes fully distributed optimization. So we've looked at the trade-offs across that. And then you can also look at optimizing caching and edge computing. This actually can be used not just for cellular, but for other networks like Wi-Fi networks or millimeter wave networks. And so this actually gets to what I call the Shangri-La of wireless network design, where we have this unified control plane that's allocating resources optimally to the different wireless networks, and also matching up the applications to the right network. So for example, if you're doing video, you would probably want that to go over a millimeter wave network if it was available, because that's a much faster network. But then if you moved away from the millimeter wave network, you would want to be handed off to, for example, the cellular network with the highest capacity. And ultimately, what you might do is just have a bunch of distributed antennas, and this unified control plane is doing the resource allocation and basically acting as the control plane for the entire network. And this is really critical for coupled networks that have really hard constraints on the requirements. This software-defined network can meet the constraints of all these different applications. If I look at wireless networks beyond 5G, my vision is really that it's going to be platforms that allow people and organizations to interact in the digital world. So with that, I'm going to wrap up and I'll take a few questions. Just say it's a very exciting time for wireless. We need these requirements that the 5G network promise is trying to deliver, and there's many interesting research challenges to solve. So with that, I'll stop and happy to take some questions.
Wonderful. Thanks so much, Andrea, for the fantastic talk. And I also wanted to congratulate you for earlier this year winning the prestigious Marconi Prize for your own contributions to this exciting area. So we have a ton of questions for you. So I'm just going to take the moderator's prerogative and ask one myself first. 5G networks are clearly exciting. You captured a lot of the excitement and potential, but a lot of people say there are a lot of barriers, particularly for the SIGCOMM community, research community, to get involved here. You know, the dominance of vendors and carriers, the cost of acquiring spectrum and installing equipment, and for many of us, myself included, a fairly limited understanding of the physical layer and the associated mathematical techniques that your community obviously focuses on. So where's the space for us here? Or is there room for us to contribute here, despite those barriers?
Yeah, absolutely. So I think that actually, you know, it is very difficult to contribute at the cellular level just because of the politics and the standardization process and the barriers to entry. But there's the unlicensed bands are really the bands that are open for innovation. I mean, both of my startups were focused on Wi-Fi for exactly that reason. And there's tremendous opportunity to innovate in the Wi-Fi space. And so what I would recommend is for people in the SIGCOMM community, first of all, you do need to partner with people that understand the physical layer because that's where a lot of the innovation is going to take place. But there's also a lot of need for innovation in the Wi-Fi network. So my recommendation for people that are looking to innovate is really looking more at the unlicensed bands than at the licensed bands.
Fantastic. A question from Dave Oran on Slack. Is it a good idea for people operating at the higher layers to still think of wireless channels as broadcast channels that can provide a big win for multicast?
So it's interesting because broadcast, I mean, wireless channels are broadcast channels, so that is how you should look at them because that's what they are. But that hasn't actually been the way that wireless networks, either Wi-Fi or cellular, have been designed. They've basically been designed as point-to-point, even though they are broadcast networks. So the only thing you get out of the broadcasting capability is that you can talk simultaneously to different users, but you're sending them often different messages. The only place that's not true is like in TV broadcasting and radio broadcasting. So I think it's not clear why that's the case, except that different users don't want the same content at the same time. So perhaps that becomes an architecture issue where you say you broadcast to this cell edge, which is breaking the end-to-end paradigm that we've always used in the internet. But you say, okay, I'm going to broadcast this information to the edge, and it will be available to users when they want it. I think that is the, you know, magic of utilizing broadcasting in these networks. But since people want content at different times, if you broadcast it out, they don't want it. And that's why it hasn't really worked as a paradigm up until now.
Great. A question on Slack from Henning Schulzerine. What parts of 5G do you consider hype or unlikely to pan out?
Most of it, you know, I think that 5G is a marketing term until it becomes a standard. And that's true of every G. So, you know, that was true of 2G and 3G and 4G. So 5G, first of all, the promise, the slide that I put up, the promise that we're going to get this very low latency and tens of gigabits per second and extremely high reliability. We probably will get to 10 gigabits per second in the millimeter wave bands. We won't get to that in lower bands. That's not ubiquitous. I mean, that's really a niche market. So 10 gigabits per second is not reality, at least in most of the places where you're going to have access to 5G. The low latency, we don't have that yet, and it's hard to see how we're going to guarantee that. Same with the reliability. So I would say most of what's promised is hype, but we can get closer to those promises. And I think that that's really the goal of 6G. But today we have, you know, 10 gigabits per second, very close to a base station, otherwise probably an order of magnitude lower than that. No guarantees on latency and no guarantees on reliability.
So another question from Slack from Nafel Yassin. In our community, we've been thinking a lot about programmability in the data plane of network devices. And do you see potential for programmability of the antennas?
Absolutely. And in fact, the antennas today are programmable in the sense that those large arrays, whether they're massive MIMO or just MIMO arrays, they're dynamically adjusting. So basically you are pointing that beam at the receiver that you're talking to. So that's one aspect of programmability. Something that I've looked at in the past, but it's very hard to do in practice, is programming the antennas to take into account everybody in the network. So you can avoid interference, not just point at your receiver, but point away from the devices that you're interfering with. And that's, again, going back to this concept that these systems are interference limited. Anything you can do to reduce interference is going to give you much, much better performance. But it's hard to do that because now your antenna programming has to take into account not just the channel parameters to your receiver, but everybody around you. And I think that's why it hasn't actually been done in practice. You can also, if you're thinking about this as a broadcast system, you can take this large array and program it so some part of it is pointing to one user, another part of it is pointing to another user. So there's tremendous opportunity to do the programming. It's easy to do in terms of changing the antenna parameters. It's hard to do the optimization.
Cool. So another question from Slack from Christian Timmerer. What in your view will be the killer app or the set of killer apps for 5G?
So I always like to say, you know, if I knew that, I would tell you I'd do a startup around it, although I think I'm done with startups, especially coming in from the team. You know, I think what we need to do with wireless networks is the same thing that made the iPhone the platform for killer apps. It's that you need to make a platform that will enable whatever app emerges as the most important one. So I can give you all kinds of applications for the Internet of Things, which is these, you know, low-powered devices that are connecting to the internet and talking to each other. You know, maybe it's security, maybe it's health, maybe it's automation. But I don't know which one of those is going to be the killer app. Some are making money today. They may all go away. There may be another one that emerges. What we need to do is build a wireless network that actually satisfies that promise of the triangle, where we can support high data rates for some applications, low latency, low energy consumption for, you know, different applications. And then the applications will emerge. And maybe there isn't one killer app or 5 killer apps, but you know, every group of users has their own favorite application of how to use the wireless network. So the way I view the network is as a platform, and we need to be able to enable a whole range of applications, and then the killer apps will emerge.
Fantastic. I got a question from the Zoom Q&A about when the first standalone 5G deployments are expected and who's going to lead in this space in terms of deployment. And I'll just add to that also, I'm curious your thoughts on private 5G and whether that will become an alternative to Wi-Fi in any particular setting.
So there already are 5G deployments, and it kind of depends on what you mean by 5G. So the new radio, which was the first part of the 5G standard that was deployed, I mean, that's already out there. You can buy devices that have the new radio. There are base stations that have been deployed that are 5G compatible. It's associated with the 5G standard. So it is out there. I think T-Mobile has been saying that they were going to do the first nationwide 5G network. I don't know exactly where we are in deployments, but there are deployments throughout the US, which is you know, probably ahead of most other countries. You can buy a 5G device today. Now the question is, you know, 5G is not like a stake in the ground, a moment in time, because it will continue to evolve until we have 6G. So if the question is, you know, should I buy a 5G radio device now, or should I wait another 5 years? I mean, the longer you wait, the more that technology will evolve. And then going to the private 5G network. So I have a hard time seeing why a private cellular network would be better than an enterprise Wi-Fi network in an indoor setting or in a campus-like setting. Because enterprise Wi-Fi gives you almost the same quality of service as cellular, but with much more bandwidth. So I know that there's a lot of talk about these private 5G networks, but I'm skeptical that they will actually take hold and be widespread.
Awesome. So we're almost out of time. Just one final question from Karen Solons on Slack. So we often think in our community about the narrow waist of IP, you know, that everything sort of is above or below that narrow waist. And it seemed like in your talk, you were proposing a sort of narrow waist at the control plane level in thinking about 5G. Is that a good architectural way of thinking about your proposal? Or do you think there is a narrow waist here in the 5G setting?
So by narrow waist, do you mean a very light control plane, or
It's something that everything builds on top of all the media below and supports all the applications above. You know, is there some
yeah,
central thing that doesn't change that everything else depends on?
you know, I think that there's kind of a Shangri-La of thinking about how you would design networks from scratch, which is what that unified control plane vision is. But the reality is that isn't how the networks actually exist today, and so it's very difficult to change them completely. Right now, networks are mostly stovepiped, and they don't have that kind of narrow waist that you described, and so it's hard to see an evolution to that point, at least in cellular, but perhaps in other kinds of networks like Wi-Fi networks, it may emerge. But I think that the reality is that there is existing platforms and existing network structures that are very difficult to rip out and put in a new structure from scratch. So I think that we're going to be with those architectures for quite a long time.
Fantastic. Thanks so much. We have a bazillion more questions, but unfortunately not enough time to get to them. So thank you so much, especially for getting up so early on the West Coast, and see you soon on the East Coast.
Yes, see you soon. Thank you very much for inviting me.
Pleasure. I'll hand over to Nick.